I will talk about the orthogonal matching pursuit algorithm. So here we have a matrix A, n by m. So typically it has many columns, and we have a vector B, and we want an approximation of B that is in the range or column space of A. So we want an approximation of B that is A times a vector here of dimension m by 1. This is n by m. But we want a sparse representation. We want this vector to be sparse, which means that we want a few non-zero components in that vector. So the task is that we want to express B or a model of B or an approximation of B using a few number of columns of matrix A. Now, one way of doing this is the orthogonal matching pursuit algorithm. And so we will initialize the set S of 0 as an empty set, and this is the residual, so R for residual, and this will be our vector, which is B. Then in each step, in each iteration, we will do the following. So we will work with the columns of A. So the notation that is used here is that if I write, for example, A and put here a set 1 and 3, for example. So this is a matrix, so this is a matrix in which you have the column 1 of A and column 3 of A. If you have A is equal to 1, 7, and 19, so this is a matrix that it has the first column of A, column 7, and column 19, and so on and so forth. So here we have a set with Q. So Q is between, so then the A has m columns, so Q is 1, 2 to m. But we exclude sk minus 1. So at the very first iteration, k is 1, s of k minus 1 is s of 0, and it's an empty set. So basically, we will use all the columns of A. In later iterations, basically, we'll use the columns of A whose indices are not included in the set S of k minus 1. So what are we doing? We are here computing the inner product of R of k minus 1. So this is the vector initialized as B with a normalized, so this is the qth column of A, but it is normalized by its L2 norm. So this is a vector with an L2 norm of 1. And so we will do the inner product. So we'll take this guy here and have its Hermitian times Rk minus 1. And then we compute the magnitude. So again, we will sweep through the columns of A. We will sweep through the columns of A, excluding the columns with indices that are contained in this set S of k minus 1. And given that S of 0 at the very beginning, this is an empty set. Now we will use the normalized columns of A. So each column, is scaled by, it's divided by its L2 norm, so that you get a vector whose L2 norm is unity. Then we will have the inner product between this normalized column of A, the qth column, and the residual Rk minus 1. And then we compute the magnitude. Then V of k, this will be the index. So this is the value of Q that gives you the maximum value of this magnitude. In other words, we will choose the index of the column such that, you know, the magnitude of the inner product of that column with RK minus 1 is maximum. This V of K will be appended to the set. So S of K is S of K minus 1, and then you append V of K. Then you now represent B using the columns of A that are contained in S of K, in this set S of K. So we do least squares. So we minimize the distance, the Euclidean distance, or the square of the L2 norm of B minus A sub S of KZ. Okay, so A sub S of KZ, basically this is A times a vector of length M by 1, such that, you know, the vector is all 0, but in the end, so if S of K, for example, is the set 1 and 8 and 9, then in the first place, we have potentially non-zero element, and then in the 8th place, position 1, position 8, position 9, and then we have zeros. Okay, so we have this least squares problem in which we minimize the square of the Euclidean distance between B and a linear combination of the columns of A, specifically the columns whose indices are in S of K. And we want to find this vector of coefficient Z, which is of size K by 1. K by 1 because the set S of K, so if K is 1, so you start with an empty set. You know, after diving into the first iteration, then your set S contains one index, then when K is 2, you have 2, and so on. So in the kth iteration, this vector is of size K by 1. So you will find the Z that minimizes this quantity here. And this Z will be the vector X of K. And then we update the residual. The residual is RK. So basically the residual is you can say it's the error. It's the difference or discrepancy between B and basically this linear combination of the columns of A that are indexed by, you know, the elements of S of K. And we keep doing this. We can, you know, do this for a specified number of iterations. So if we do this for L iterations, then we end up with a representation of vector B, basically using 30 columns in matrix A, or rather than fixing the number of iterations, we can measure the L2 norm of the residual vector, which is the error, the difference between B and basically this guy here that is living in the column space of A, and that acts like an approximation for B. So we have this error vector, and we measure, you know, perhaps it's L2 norm, and then, you know, wait for this norm to drop below a specified threshold. Now, when I say something like this, is it like guaranteed that this L2 norm will decay? And if it decays, will it decay to 0? Will it decay to 0? Note that to decay to 0, you will have, you know, to have a condition which is that vector B is in the range of A. So if vector B is in the range of A, then it is possible that you can reduce the residual vector to 0, okay, after perhaps a very large number of iterations. So basically, this video is about investigating the convergence of this algorithm, the orthogonal matching pursuit algorithm. Okay. So let's start by thinking about this optimization problem. And this optimization problem is a standard optimization problem. Again, it's just least squares. And, we can just write down the solution, or like if we do things in slow motion, then we can compute the gradient of this objective function. So the gradient will be minus 2 a s of k Hermitian, and then b minus a s of k z, and this is equal to the all zero vector. Okay, and then we can just remove this minus 2. Okay, and then when we equate to 0, actually we will obtain our solution. So this z now is the optimal solution, which is s of k. Before writing down an expression for x of k, note that if you solve for x of k, okay, you find, okay, so let's actually do it. So a s of k Hermitian b is equal to a s of k Hermitian a s of k x of k. And then, assuming that a s of k Hermitian a s of k is invertible, then x of k is a s of k Hermitian a s of k inverse, and then we have a s of k Hermitian b, which is, like, again, the standard least squared solution. And so basically for invertibility, we need the columns. So the selected columns must be linearly independent. So this matrix is invertible if and only if the columns of a sub s of k are linearly independent. Now, the residual itself is updated by this quantity. So this is the new residual in the kth iteration. And so this is b minus a s of k, a s of k, and then we will put this one here. B, and this is, we can write it as b, which is n by 1. And then here we have a matrix which is identity n by n minus a s of k Hermitian a s of k inverse a s of k Hermitian. Note that this is a famous matrix. This is an orthogonal projection matrix. This is an orthogonal projection matrix onto the range of ASK perpendicular. So this matrix projects orthogonally onto the subspace that is orthogonal to the column space or the range of matrix A sub S of K, which means that if you take this matrix and multiply it by any vector in the range of A sub S of K, you will get 0. Okay, so so this is R of K, and let's emphasize this, that R of K is perpendicular to the columns of A sub S of K. Note that this is also clear from here. Okay, so if you cannot see it from the orthogonal projection matrix, this is clear from here. That basically, once you put here the optimal solution, then this is the residual R of K, and you can see that the inner product of any column in the matrix A sub S of K and the residual vector R of K is equal to 0. Okay, so again, you can see it also from here. And this is very important. Now, what is the L2 norm squared of the residual? So this is an extremely important quantity. So basically, this is what we are interested in this convergence analysis. This is a quantity that we wish to decay to 0 if vector B is in the range of matrix A. So this is basically the quantity that we will track and make sure that it is, it decreases with iterations and perhaps to 0 again if B can be, perfectly expressed as a linear combination of some columns in matrix A. Now, what is the L2 norm squared? So, if you call this matrix psi, then, the L2 norm squared of this thing will be, so psi B L2 norm squared. So this is B Hermitian, psi Hermitian, psi B. But this is an orthogonal projection matrix. So its Hermitian is itself. So psi Hermitian is psi, and it is an idempotent matrix because psi is an orthogonal projection matrix. So this is B Hermitian psi B, and this thing itself is B Hermitian R of K. Okay, so the general rule will be that the L2 norm squared of the residual vector is vector B Hermitian by R of K. So it's the inner product of the residual vector itself and vector B. Okay. Now, the trick here is that we will consider an update equation for vector x that is suboptimal. Okay, so what do I mean by this? I mean, we will define, let's say, alpha is the argmin of eta, and then we have here b minus a s of k minus 1 x of k minus 1 minus a v of k, and then we have here an eta, and then this is the L2 norm squared. Let's see what is going on here. So in the orthogonal matching pursuit algorithm, what we are doing is that once we obtain the new index, the new column that we are using in matrix A, it is appended to this set to get S of K, and then we obtain this k-dimensional vector Z. This will be X of K. So we minimize. it's again, we have like if you want to represent X using, sorry, if you want to represent B using K columns in matrix A. So here we are optimizing over the coefficients, the K coefficients that are needed so that we approximate B as A sub S of K times a K dimensional vector. We are optimizing over the K coefficients here, or the K elements of vector Z. And the optimal solution will be X of K. So what are we doing here? We are basically saying that as if X of K is X of K minus 1 and one new component, or let's say one new coefficient, to be multiplied by the new or newly selected column. So basically eta here is just a scalar, okay? So remember that you have A, so these, what is S of K? S of K is the union of set S of K minus 1 and V of K. So we have this set, and what we do is that those guys are copied from the previous iteration, and then there is only one component that will be optimized. So this is worse than what we are doing in the orthogonal matching pursuit algorithm, because here, we want to crush the residual vector as we can by minimizing over the K elements of vector Z, which will be the K coefficients that multiply K vectors in matrix A to generate an approximation for vector B. But what we are doing here is that we are reusing the previous vector X of K minus 1, and we are just optimizing over the new element, which is 8. Now, in practice, we can have a more simplified algorithm than OMP. So we can basically do a complexity accuracy trade-off. So this is actually another thing that we can do. This will be another algorithm, again, in which we simplify the calculations, reduce the complexity, and of course there will be a price. The performance will not be as good as in orthogonal matching pursuit. But this, in any case, this is a step that we are doing here conceptually, so that we can have a bound on the L2 norm squared of the residual vector. Okay, so we don't really need to do this. If we do it, then again, the residual, so the minimum, is denoted R tilde of K squared. And what do we have? We have that R of K squared is less than R tilde of K squared. So this is the quantity. This is the quantity that we are interested in. And now we are constructing an upper bound on this residual. That is, so we construct this by using a worse algorithm. So what is the algorithm? Don't basically optimize over K coefficients to multiply the K columns of A whose indices are in this set S of K. Just fix K minus 1 of them and just focus on one of them. Okay, so again, this is a step. So this is here to have an upper bound on the quantity of interest which is the L2 norm squared of the residual vector R of K. Now again, if we differentiate, if we get the gradient, so this now will be alpha, and this is equal to 0. Note that this thing is R of K minus 1, and hence alpha is equal to K Hermitian times this guy, R of K minus 1, and then note that alpha is multiplied by this guy times this guy, so this is the L2 norm squared of this column from matrix A. So this is alpha, and R tilde of K is equal to RK minus 1. RK minus 1 is B minus A sub S of K minus 1 X sub, this superscript K minus 1. And this residual is R of K minus 1 minus, then we have this vector and this vector, okay, R of K minus 1. And here downstairs we have this nice looking L2 norm squared. Okay. Again, there is a projection matrix, right? So there is identity minus this thing. So this is an orthogonal projection matrix that projects orthogonal to this this vector. Okay. Now compute this guy. Just do it like this. So take the L, the L2 norm squared, and it will be the L2 norm squared of this vector minus the L2 norm squared of that vector. This will be K Hermitian RK minus 1 magnitude squared divided by this quantity. Okay. Now, again, this residual, it comes from this idea that at least in the proof, we can imagine a worse algorithm to obtain vector X. So this worse algorithm will keep the K minus 1 coefficients that we have and will append just one new coefficient rather than optimizing over the K components, the K coefficients that are needed in iteration K. And as I said, that the idea is that we can now write down this upper bound. And this upper bound tells us that the L2 norm squared of the residual, right, the L2 norm squared of the residual at iteration K is less than or equal to the L2 norm squared of the residual at iteration K minus 1 minus a number. Okay, so note that this L2 norm squared is strictly less than this L2 norm squared if this inner product is non-zero. So the L2 norm, this L2 norm is a non-increasing function of K. This is good news, but it is not enough because it can be non-increasing function, but it converges to a value that is not small enough. Okay, again, our hope is that the algorithm actually, if vector B is in the column space of matrix A, that this guy will converge to 0, which means that after, you can always reduce it beyond any given threshold. How can we proceed from here? Our focus will be this guy. So let's recall a result. See this result from early in this video. I will just use it for vector rk minus 1. So this guy, rk minus 1, its L to norm square, is B Hermitian rk minus 1. Now let's do the the general case. Okay, so the case, there is a case in which you can say, well, B in fact is living in the column space of A, but let's assume that B is a vector B tilde in the range of A plus B minus B tilde, and so this is not in the range of A. Now what is B tilde? B tilde is A beta. A times vector beta. And what is beta? Beta is the minimum, and here m by 1, of B minus A gamma L to norm square. See, what you are doing here is that this is the representation of, or the approximation of, the B vector in which you use all columns of A. All columns. This will give you the least residual from the point of view of the residual. Okay. But note that, why not just doing this? Note that this gamma vector, is not necessarily sparse. Okay, so perhaps it's good actually to review the main objective of what we are doing. So we want an approximation of vector B. We will basically construct this approximation from the columns of A, sort of column by column, and stop after a few iterations, or after we have the L to norm of the residual going below some given threshold. The idea is that we want this vector here to be sparse, which means that, again, we want our representation to use a few columns of A, so that this vector is sparse. This is the objective. So doing this problem, which I wrote down here, so here what I'm doing is that I am really getting the best approximation for B in the column space of A, using every column in A, but vector gamma here, after it's optimized to get the vector beta, who said that vector beta will be sparse? So the idea here is that we want a few coefficients. Why do we want a few coefficients? Think of this like compression. We want to approximate vector B by few numbers, a few set of numbers. We are trying like to compress. The idea, so we are really interested in approximating B, but it's not that, it's just that we want the minimum residual using all columns of A. We want a compact representation. So again, this one, if you want to solve it, so this is the gradient vector B minus A gamma. This is equal to 0 by 1. Okay, and then so we have here that this now will be beta, because if you equate to 0, then this will be the solution. And as you can see from here, that B minus A beta, this is B minus B tilde. Okay, and so we can eliminate this guy, and if you multiply by beta Hermitian, 0, and this is B Hermitian B, sorry, B tilde Hermitian B minus equal to 0, which again is a known result, which is that if you solve this problem, basically these two guys will be orthogonal or perpendicular to one another. So this inner product is equal to 0. So it's just the orthogonality principle. Okay. So what I will do is that I will assume this. I will assume that perhaps we cannot really get this thing into 0, and there is like this, perhaps this guy, it has a non-zero norm because B is not in the range of A. Let's decompose this B as B tilde. So this is A beta. This is the part in vector B that is in the range of A, and then there is this part of Hermitian RK minus 1. Now note that this thing is an L2 norm squared. Okay, so this quantity is real valued and non-negative. So there is an inner product here, but it is, again, because of this equality, it is a quantity that is real valued and non-negative. So it won't harm us if we insert a magnitude, and then we can basically split into these two terms, and then we can apply the triangle inequality, and so this is less than B tilde Hermitian RK minus 1 plus this guy here. And then we need to have upper bounds. So for this one, I can upper bound by Cauchy-Schwarz. So this will give the L2 norm of this vector, L2 norm of vector RK minus 1. And then again, I can use this idea that, if you have two numbers, two real numbers, alpha and beta, then basically 2 alpha beta is less than or equal to alpha squared plus beta squared, right? Because if you move this, so this comes from alpha minus beta squared is greater than or equal to 0. So this product here is less than half the square of this guy plus half the square of this guy. And now we need to work on this one. So for this one, we have we can write down this as beta Hermitian, A Hermitian, RK minus 1. Now this is a summation G from 1 to M. So remember that A is of size n by m, so A Hermitian is of size m by n. And so this is beta J. And then we have beta J, so the jth component in this vector is multiplied by the jth component here in this vector. And so the jth component will be the jth column of A Hermitian times RK minus 1. And what we'll do is that we will divide by the L2 norm and multiply by the L2 norm. Okay. And then we will have the triangle inequality again. So this is summation J from 1 to M, magnitude beta J, and the L2 norm, this is J, is here. And then we have this quantity. K minus 1 over L2. Now, we want to further upper bound this, and we now will focus on this friend here, because this is an inner product, or it's the magnitude of an inner product between Rk minus 1 and the jth column of A after normalizing it. So let's go back to the algorithm. Now, our algorithm starts actually by doing this, by computing a similar quantity here. So but you know, in the algorithm we work with the columns whose indices are not in the set Sk minus 1. But basically we compute this magnitude of an inner product and then choose the maximum. And then we know now our new column. So here is the idea. If J is in Sk minus 1, if J is in Sk minus 1, then A J Hermitian Rk minus 1 is equal to 0. Remember, we are solving, we have orthogonality, right? We are solving a least squares, we are solving a least squares problem. So again, we did this, we get upstairs. So here it is. So you can see it from, you know, just writing down the gradient vector, and you'll find that this matrix, the Hermitian of A sub S of K times the residual vector. So here we have K, here we have K, and this inner product is equal to, which means that each column in this matrix A sub S of K is perpendicular to R of K. So here we will use this fact. So if we are talking about a column here, and this column is in A sub S of K minus 1, then the column is orthogonal to R of K minus 1. So there are terms here that are 0. We can just, you know, we can just ignore them. They are 0. And then we work with the other columns. And what is the column that gives this quantity its largest value? It is, from the algorithm, it is V of K. Okay, so what we will do is that we will upper bound this by a V of K, because by definition, V of K is the argmax of you know, this quantity after we exclude the columns that are in Sk minus 1. So this is AVK Hermitian R of K minus 1. And so this will be upper bound on all those guys. And we can have the full sum here. Okay. And let's call this guy psi or something like this rather than moving with it. So now we have an upper bound, which is psi times this quantity. So let's go back here. This will be an upper. So again, to recap, we have this L2 norm squared of the residual vector Rk minus 1, and we split vector B into the component A beta or B tilde, which is in the range of matrix A, and then there is another component B minus B tilde, which is not in the range of A, and we split this into two terms. For one term, we upper bounded by the Cauchy-Schwarz inequality and by the inequality that for two real numbers, the square of alpha minus beta is greater than or equal to 0. Then we took this term here, which involved A beta or B tilde, and we upper bounded using basically how the algorithm works, how the orthogonal matching pursuit algorithm proceeds. So let me now write the result. So after doing all these things, this is less than or equal to. So one branch gave us this thing. And then we have this guy. then we can rearrange. So we have psi, or we have this k Hermitian rk minus 1 over e of k to norm. This is greater than or equal to 1/2 of r of k minus 1 squared minus b tilde squared. Note that this is a non-negative quantity. This is a non-negative quantity because what is this thing? This is the residual. This is the L to norm squared of the residual. If you use k minus 1 columns in A, this is the residual if you use all columns of A. Okay, so this is this problem here. So if you use all columns of A, this will be the residual vector, and what we have here is its L to norm square. Definitely, if you use all columns in A, you'll get something that is smaller than this one. So this is guaranteed to be non-negative, and so we can peacefully square basically both sides of this inequality. I think I forgot this psi guy. So here also we have 1 over psi. So this will be 1 over 4 psi squared, 1 L to norm squared minus tilde squared. So now we have an upper bound on this guy, or if we multiply both sides of this inequality by -1, then we have, we have a lower bound on this guy, and if we multiply both sides of this inequality by -1, we will have an upper bound on the negative of this guy. Why is this guy interesting? Well, it's interesting because this is the guy that is here. This is okay, and it is here. Okay. So now we have a good upper bound on the L to norm squared of the residual vector r of k. Okay, so we can go upstairs and copy. So this r of k squared is now less than or equal to. So there is this term, and our again, this is a lower bound on this quantity. We have it with a minus sign. So with a minus, we have an upper bound which looks like this. Finally, we will subtract this quantity. Again, what is this quantity? It is the minimum residual if you use all columns of A in your attempt to represent or approximate or model vector B. So it is like, so the residual will never go below this number, because this is the residual if you use all columns. Okay. So it is nice if we basically write down things like this. So this is b minus b tilde squared, squared like this. And here, of course, I subtracted here, so I will get this guy minus this guy. I think I forgot. So this guy is squared, right? So we have this one, and then we squared here, so there is a square here. And so we have this guy, and then we have minus 1 over r squared, and then we have this squared, which is, oops, rk minus 1. Let's say that this is 5k. So this is 5k minus 1. Note that we have this term here, and we have it's a square. We can take it as a common factor. So this is 5k minus 1 over d. We have this recursive inequality, and we want basically to have 5k on one side and then the other side, to be something that depends only on k. So how can we proceed from here? We are very close. The first thing is like to investigate this function phi. So what is phi of 0? So phi of 0 is, initially you are not using any columns, and the residual vector is just vector b itself. And so this is b squared minus b tilde squared. And so this is b tilde plus b minus b tilde L2 norm squared. Remember that orthogonality dictates that these two vectors are orthogonal to one another. And so this L2 norm squared will give us this guy squared plus the L2 norm squared of this other guy. But then there is a minus sign. And so there is cancellation, which is good. And so we have the L2 norm of b tilde squared. L2 norm of b tilde squared. Okay, so I mean, let's just try to do it. So this is beta, right? This is a beta. So this is beta Hermitian a Hermitian a beta, which is, you can add a magnitude. Again, we are talking here about something that is real valued and non-negative. And we have a quadratic form here with vector beta and matrix A Hermitian A. And so this is a sum, let's say j from 1 to m, and then L from 1 to m. And this is j conjugate beta L. And then we have element here, jl. So this will be a j Hermitian. And then we have a L, like this. And now we can apply the triangle inequality. And if we apply the triangle inequality, then this thing becomes magnitude beta j, magnitude beta L. And perhaps we can apply the triangle inequality, and together we have Cauchy-Schwarz, a valuable friend here. So again, when you apply the triangle inequality, the magnitude of the sum is less than or equal to the sum of the magnitudes. And then when you apply the magnitude to the summand here, you will have the magnitude of this inner product. And the magnitude of the inner product is hour bounded by the product of the L2 norms. So this will be the L2 norm of J and then the L2 norm of L. And so this is nothing but the summation J from 1 to M, beta J, A J, L2 norm, and then you square this guy here. And this summation is the quantity that upstairs we called psi. So this is actually psi squared. And then moving from this step to that step, we called 4 psi squared as d. And so this means that this guy is d over 4, which means that phi of 0 is upper bounded. Again, where is the upper bounding? The upper bounding comes from here by applying the triangle inequality and the Cauchy-Schwarz inequality. So phi of 0 is upper bounded by d over 4. And I think we all agree that d over 4 is less than or equal to d, or d over 1, which is d. Now, using our recursive inequality, we have phi of 1 is less than or equal to phi of 0, and then 1 minus phi of 0 over d. Note that this quantity is less than or equal to 1, and this quantity from here is less than or equal to d over 4. So this one also is less than or equal to d over 4, which is strictly less than or less than equal to d over 2. d over 2. So you can see where we are going. We are trying to have an upper bound on phi of k. And it seems that irreasonable upper bound is that 5, so 5 zeros upper bounded by d over 1, 5 1 upper bound by d over 2. So perhaps phi of k is upper bounded by d over k plus 1. Okay, so let's basically do induction. So let's assume that this is true. Suppose this is true, and this is 5k, and this is the right hand side of the recursive inequality, 5k 1 minus 5k over d. So this thing is like this, right? So it is 0 at 0, and then when 5k is 0, this is 0. When 5k is d, this is 0. And then this thing, it peaks here at d over 2. And so we are basically this transfer function between 5k and 5k of 1 minus, it is monotonic. We are working basically on this part. We are working on this part, which means that phi of k plus 1 is less than 5k 1 minus 5k over d. So this is the function, and this function is upper bounded by the maximum value of phi of k. Okay, so this is upper bounded again because we are working on this part here. So this is less than or equal to, so this is the induction assumption that this is less than d k plus 1, and then 1 minus, so here we have d over k plus 1 over d, that's 1 over k plus 1. And then this is k d over k plus 1 squared. And then we know that the k plus 2 by the AMGM inequality, this is greater than 2 square root k k plus 2. And so these two guys are 2k plus 2 divided by 2, that's k plus 1. And so k plus 1 squared is greater than or equal to k plus 2. And so 1 over k plus 1 squared is upper bounded by 1 over k plus 2. So k over k plus 1 squared. Okay, so we have this, that 5k plus 1 is less than or equal to, and what we have is d over k plus 2, which is exactly what we want. We want it to be d, and then the index here, it's here k plus 1, and then plus 1. So this is a good result from the recursive inequality. So let's now, what is 5k? Oh, this is the result now that we have. That remember that 5k is the residual squared minus this residual that you cannot beat, because again this is something that you are stuck with if b happens to be not fully living in the range of a. So now we have the bound, so r of k to norm squared is less than or equal to, move this to the other side. So again, this is something we cannot control, but if b is in the column space of a, that's it. I mean, this will be 0, and this is the good thing. We have here this d. Okay, this d, don't forget the d, I think it was like 4 psi squared or something like this, 4 psi squared. This d is like 4 psi squared. And what is psi? Psi is this summation j from 1 to m, magnitude beta j, magnitude, so this is the L2 norm of the jth column of matrix A. And remember what's the beta? The beta is, if basically beta tilde, which is the component of vector B in the range of A, is equal to A beta. So it is this vector. Is vector here, and those are its components. So we have this d, it's some positive number divided by k plus 1. And so as you can see, if b is in the range of a, then this is what we have, and the residual is upper bounded by d over k plus 1, and we can make it small by doing enough iterations. Or as I said at the beginning, we can perhaps fix the number of iterations. Again, it depends on what we are exactly doing. Thank you.